Nearly 40 light-years away, astronomers are studying a planetary system unlike almost anything we've seen before. Around a tiny red star, 7 rocky worlds are packed into an incredibly small region of space. And one of those planets has become especially important. It's called TRAPPIST-1e. It's about the size of Earth, appears to be rocky, and receives enough energy from its star to make scientists wonder whether liquid water could exist there under the right atmospheric conditions. That possibility made it one of the most fascinating worlds in the search for life beyond Earth. So naturally, astronomers pointed the James Webb Space Telescope toward it. Webb is one of the most advanced space observatories ever constructed. Its instruments were designed to study distant galaxies, stars, and planets, and, importantly, to analyze the atmospheres of worlds orbiting other stars. The hope was simple. Look at TRAPPIST-1e. Study the light passing through its atmosphere. Search for molecules such as water vapor, carbon dioxide, methane, and other gases. And perhaps discover whether this distant world could actually be habitable. But instead of getting a simple answer, scientists encountered a much harder problem. The planet isn't necessarily hiding the evidence. Its star is. TRAPPIST-1 is a red dwarf, much smaller and cooler than our Sun. Yet despite its small size, the star is extremely active. Its surface changes. Dark star spots appear and disappear. Bright regions evolve. And powerful flares can erupt from its surface. For astronomers trying to detect the incredibly tiny atmospheric signature of a planet, that activity is a nightmare. To understand why, first look at the planetary system itself. TRAPPIST-1 sits roughly 40 light-years from Earth. Across the entire Milky Way, that's a relatively short distance. Our galaxy is approximately 100,000 light-years across. And inside this nearby system are 7 rocky planets. They orbit so close to their star that the entire planetary arrangement could fit inside the orbit of Mercury in our solar system. The fastest planet completes an orbit in roughly a day and a half. The outermost planet takes less than 20 days. Normally, planets this close to a star would sound impossibly hot. But TRAPPIST-1 is far cooler and dimmer than our Sun. That moves the region where liquid water could potentially exist much closer to the star. 3 planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1 are located in or near this potentially habitable region. That's what made the system so exciting. Not just one interesting planet. 3 worlds worth investigating. And the discovery itself was remarkable. Astronomers first detected planets around TRAPPIST-1 using relatively small telescopes. Then NASA's Spitzer Space Telescope spent weeks observing the system. Those observations revealed additional planets that had previously gone unnoticed. By 2017, scientists had identified all 7 worlds. But there was another fascinating feature. The planets aren't orbiting randomly. Their orbital periods are connected through a resonant pattern. Their gravitational interactions cause tiny variations in when the planets cross in front of their star. These changes are extremely small. But by measuring them carefully, astronomers can estimate the masses of the planets. And those measurements showed that the worlds are rocky rather than giant gas planets. TRAPPIST-1e became one of the most interesting members of the system. It receives around 2/3 as much stellar energy as Earth receives from the Sun. Its size is similar to Earth's. And its location makes it a prime candidate for atmospheric studies. That's where Webb comes in. Here's how the search works. When TRAPPIST-1e moves across the face of its star, some of the star's light passes through the planet's atmosphere. If gases are present, they absorb particular wavelengths. Those missing wavelengths can create patterns in the spectrum. Scientists can then compare those patterns with laboratory models and determine which molecules might be present. It sounds straightforward. But there's a problem. The planet's atmospheric signal is incredibly faint. The star's own changing surface can produce a much stronger signal. Imagine trying to identify a quiet voice while standing next to an enormous speaker. The voice is still there, but the speaker is overwhelming it. That's essentially what astronomers are dealing with. And stellar activity isn't just random background noise. Star spots and bright regions can create spectral patterns that resemble atmospheric signatures. That means scientists can't simply delete the unwanted signal. They have to model what the star itself is doing. During observations of TRAPPIST-1e, stellar activity made the problem even harder. A strong flare occurred during one of the observations, introducing additional contamination into the data. The result? Scientists couldn't confidently determine whether TRAPPIST-1e has an atmosphere. But observations of the other planets have helped narrow down the possibilities. TRAPPIST-1b, the innermost planet, has been examined with Webb's infrared instruments. The observations strongly disfavor the presence of a thick atmosphere. Instead, the evidence is consistent with a hot rocky world with little or no substantial atmosphere. TRAPPIST-1c has produced similar evidence. A dense atmosphere appears increasingly unlikely. TRAPPIST-1d has also failed to provide the atmospheric evidence scientists hope to find. Its observations have not produced convincing detections of several important gases. Together, these results suggest that the inner planets may have experienced significant atmospheric loss. And that makes TRAPPIST-1e even more important. If its neighbors lost their atmospheres, perhaps TRAPPIST-1e did too. But maybe it survived. Maybe it retained enough air to keep its surface environment stable. We simply don't know yet. There was another intriguing development. Some atmospheric models of TRAPPIST-1e appeared to fit the observations slightly better when methane was included. That was interesting because methane can play an important role in planetary chemistry. But then scientists encountered another complication. The star itself can contain methane-like spectral features. Because TRAPPIST-1 is an unusually cool red dwarf, molecules that normally wouldn't survive in the atmosphere of a sun-like star can exist there. So a spectral feature that looks like methane might not come from TRAPPIST-1e at all. It could be coming from the star. And that completely changes the interpretation. The apparent methane signal could be planetary. Or it could simply be another example of stellar contamination. Current observations aren't strong enough to confidently separate the two. That leaves scientists with two broad possibilities. Scenario 1. TRAPPIST-1e could be a barren rocky world that lost most or all of its atmosphere because of its star's radiation. Scenario 2. It could possess a relatively thin atmosphere that is simply too difficult to detect through the star's changing light. A thick, hydrogen-rich atmosphere is much easier to rule out. But a thin atmosphere remains possible. So how can scientists solve the problem? They came up with a clever idea. Use another planet as a reference. TRAPPIST-1b is particularly useful because its observations indicate that it doesn't have a substantial atmosphere. That means most of the spectral features seen during its transit should originate from the star. In other words, TRAPPIST-1b can act like a natural calibration target. Scientists can observe TRAPPIST-1b and learn what the star's contamination looks like. Then they can compare that information with observations of TRAPPIST-1e. The goal is to remove the stellar contribution and see what's left. If a signal survives the correction, it could potentially belong to TRAPPIST-1e. It's an elegant idea. But once again, the star refuses to cooperate. The stellar surface can change between observations. A new flare can appear. Star spots can evolve. Bright regions can move. So the contamination measured during one planet's transit may not perfectly match the contamination present when another planet crosses the star. That's why scientists need repeated observations. The more data they collect, the better they can distinguish temporary stellar events from genuine planetary signals. And this isn't the only solution being developed. Future missions could attack the problem from several different directions. NASA's Pandora mission is designed to monitor exoplanets and their host stars together, helping scientists understand how stellar variability affects planetary measurements. Meanwhile, next-generation ground-based telescopes will have enormous collecting areas and extremely high spectral resolution. That could allow researchers to separate planetary and stellar signatures more effectively.